All right, welcome to Unit 8, Day 3. We are taking a look today at special right triangles. And so before we do a lot of writing, this first part of the video you just need to watch because I'm going to talk about where we get these triangles that we call special right triangles. So we're going to start with a square. Okay, this is a perfect square. A lot of things we already know about this. It has 4 sides, 4 right angles. That's kind of one of the important parts you need to pay attention to, is that all 4 of these angles are right angles. Okay. All right. And all 4 sides are the same length. Okay. Doesn't matter if they're opposite sides or consecutive sides, they're the same length. And so we're going to use this. I know the lesson's over triangles. So what I'm going to do, I'm going to show you kind of where something comes from that we're going to use later on in the lesson. I'm going to take this square and I'm going to actually cut it in half so that it forms 2 congruent triangles. Okay, and so when we do that, we get these 2 congruent triangles, and I want to talk for a minute about what happens when we cut along that line. Okay, we still have all 4 sides are the same. That means these sides are both the same, so I can call them both x. All right, and these angles, okay, let's just maybe take a look at one of them. These angles are each half of what they used to be. Okay, they used to be a right angle, 90 degrees, so each of these angles is 45 degrees now. And then this one is 90, and you'll notice that all 3 of these add up to 180 degrees. 90 plus 45 plus 45 is 180 degrees. Okay, and so what we get is a special triangle because both the sides are the same length, and we get these special angle measures. And we're going to talk about this. This is called a 45-45-90 special right triangle. Okay. And there's another kind of special right triangle we're going to use that comes from originating in a shape like this. This is a triangle, but this is an equilateral triangle. In an equilateral triangle, all the sides are the same. Okay, they're all the same length, and all of the angles are 60 degrees. So they're all congruent to each other. They form 60-degree angles. Okay? So I'm going to cut this in half to form another one of our special triangles. I'm going to show you how we do that. Okay, and that creates these 2 triangles, and I cut it in half this way on purpose so that you could see this. Okay, this creates a right angle when I make that cut. If I cut it directly down the middle, that has to be a right angle, and this is 60 degrees. This top angle used to be 60 degrees, but I cut it in half, so now it is 30 degrees. And that's kind of tough to see, but I'll make this clearer later. So this side of our, used to be side of an equilateral triangle, is now the hypotenuse of a right triangle. And this side down here at the bottom is half of what that side was, so it's x over 2. And then we can talk about the relationship to what this side length is in a little bit. This is another kind of special right triangle we call a 30-60-90 triangle. So that's where they come from. They come from these exact shapes, starting with an equilateral triangle. And then the other one, the 45-45-90, coming from a square. All right, so that takes us into our notes when we start to talk about the relationships of the sides of these special right triangles. Now, normally when we talk about the side lengths of a triangle, in order to work these out, we need to use the Pythagorean theorem. And we would need at least 2 out of 3 sides. But because of the special relationship of these 2 triangles, we can actually figure out a lot of information just from one side when we memorize these patterns. And you do have to memorize these facts. Okay, this is not something I can give you on a reference sheet for a quiz or test. You have to memorize this. Okay, so first of all, in a 45-45-90 triangle, both of these legs, remember they used to be sides of a square, so they're both the same. So let's call them both x. Okay, and if I use Pythagorean theorem, I actually can figure out what this is. And I'm going to explain that to you, that we can call the hypotenuse x square root of 2. Again, you need to memorize this. Whatever the legs are in this special right triangle, remember the legs of a right triangle make up the right angle. So whatever the legs are, when they're the same as each other, the hypotenuse is just the leg length times the square root of 2. And I'll show you how we get this from the Pythagorean theorem later on in class. Okay, so make sure that you have this down. And in a 30, 60, 90 triangle, remember that the hypotenuse was the side of an equilateral triangle. So when I cut that in half, this ends up being half of the hypotenuse. So I'm actually going to call the shortest one x, so I don't have to work with fractions as much. And then to get the hypotenuse length, it's just twice as much, so it's 2x. And when we go through and use these in our Pythagorean theorem, we can find the length of this in terms of x also. And I'm going to explain to you that that is x, this short leg, times the square root of 3. Okay, so I'm going to express all these things to you and write down, but these are some facts we need to memorize so we can use them in our problems. Okay? All right, so in a 45, 45, 90 triangle, the legs are both x. Okay, we can just call them x or n or any other variable, but the legs are both the same. So if I define the leg based on that, then the hypotenuse, remember hypotenuse is the side that is across from the right angle, is x times the square root of 2. Okay, and remember, in this case, the 45, 45, 90, the legs are congruent. The two equal sides are the legs. You can see it a little better. Okay? Now, in a 30, 60, 90, we have a little bit different relationship. Okay? We have a shorter leg and a longer leg, and that's the terminology we're going to use. In this case, we call the short leg x to help us understand the relationship. And the long leg is that same short leg times the square root of 3. And then the hypotenuse is just twice the short leg. Okay? And in this case, the shorter leg is across from the smaller of the two acute angles. The short leg is opposite 30 degrees. And the long leg is opposite the 60-degree angle. And that helps you understand which one's supposed to be which. But you'll always be able to tell which is shorter and which is longer. And then the longest side itself, the hypotenuse, is 2x. All right, so let's try some examples. So in our first example, we've got a right triangle. The two sides that make the right angle are the legs in this case, and notice that this is a 45-degree angle. Now, you're often going to see only one of these marked, but if this is 45, the other one has to be 45. Okay, so this is a 45, 45, 90. We know the legs are both the same. Okay, legs are congruent. So I already know what x equals in this case. Since this leg is 8, the other leg has to be 8. And I don't need to use the Pythagorean theorem here because I'm using these facts. So to find out what this hypotenuse is, I'm going to have to take the leg times the square root of 2. Well, in this case, the leg is 8 times the square root of 2. That is already simplest radical form, so I just refer to y as 8 square root of 2. All right, let's try one more example. Okay, now, I will say, ignore my little mark here. That was an accident. Don't worry about that. That's not part of the diagram. Number 2, we have a right triangle, and you'll notice these markings mean these angles are congruent. That tells you they have to both be 45. You may not see the 45 written in there, but if they are both marked congruent, they have to be 45 degrees. And this time they give you the hypotenuse, which is 19. Remember that the hypotenuse is the leg times the square root of 2. So to find the legs, we actually have to work backwards here. Okay, we know that 19 is what we get when I take x and multiply it by the square root of 2. So I'm going to take that relationship. Instead of the word hypotenuse, I'm just going to write 19 equals, and then x actually is the leg here, so I can express that x radical 2 is what that equals. But this is just an equation. I can solve for x now. I have to get x by itself. Remember, this is x times the square root of 2. So to get x by itself, we need to divide both sides by radical 2. Okay, so those cancel. So x equals 19 over square root of 2, which, if you'll remember back to our simplifying radicals lesson, we cannot leave that way. In order to fix this, we have to take the top and bottom by the square root of 2. Okay? So if I take 19 over the square root of 2 and multiply by radical 2 on top and bottom, 19 radical 2 ends up on top, so I'm going to write my answer over here, over, and root 2 times root 2 is just 2. That cannot simplify. 19 is an odd number, 2 is even, so we cannot divide that. So that is your answer for x, and since y is the other leg, that's also the answer for y. Okay? It seems a little complex. Now you could divide this out and find a rounded answer for each, but we're going to write these answers in simplest radical form for this lesson. All right, let's move on and do a couple examples. These have both been over 45/45/90s, so we're going to move on and do another couple from 30/60/90s. Okay, give yourself a little bit of time to draw this diagram and write this down. If you need to pause the video, go ahead. But we should be ready to go ahead and tackle this problem. We have a right triangle where one angle is 60 degrees. They won't necessarily write the other one in, but if this angle is 60, 90 plus 60 is 150, and 180 minus 150 is 30. That makes this a 30/60/90 triangle. So we're going to use the relationships from 30/60/90. The hypotenuse, the slanted side across from the right angle, is twice the radius. So I can find y easily. Okay? Y equals 5 times 2, because we're going to double it, or 2 times 5. Either way, it means the same thing. So that we know that y has to equal 10. But x is what we consider to be the long leg. The long leg is the short leg, 5, times root 3. I know that 5 is the short leg. For 1, it's drawn shorter. For 2, it's across from what would be the 30-degree angle. And so 5 is the short leg. So to find the long leg, we just take 5 times the square root of 3. And we leave our answer written that way. Okay? One more example. All right, in this triangle, be careful that you set this up correctly. We have one leg marked x, the other leg marked 9 root 3, and this is a 30-degree angle. Remember, the short leg is across from the 30-degree angle always. So if this is 30 degrees, then that makes this 60 degrees. So x is your short leg. Okay? You can even make a note if you want to. Okay, x is the short leg. So since the long leg is 9 root 3, remember that the short leg times root 3 equals the long leg. So I could even set up an equation. 9 root 3 equals the short leg, x times root 3. I want you guys to notice that all you're supposed to see here is that x has to equal 9, because there's a root 3 on both, and we can divide by root 3 and do it algebraically and cancel them out, but we should just get that x is 9. Okay, and then we take the short leg, y has to be the hypotenuse then, and we take that short leg 9 times 2, which is 18. And so we found those using our rules for special right triangles. We're going to do a lot more practice in class together, but this is an introduction to that lesson.